Welcome back to another lecture from organic chemistry. We are talking about electrophilic substitution. Now, we said anything that increase the activation energy will drop rate of the reaction. And if the activation energy goes down, reaction will be faster. Okay. And now we are talking about electrophilic substitution. When it comes to electrophilic substitution, we will have a positive charge. Okay. Positive charge. We need to drop the positive charge down or distribute the positive charge to favor the reaction. So anything that is distributing the positive charge over more than one element, it will speed the reaction. And if exaggerating the positive charge, it will slow the reaction. And now let's talk about electron withdrawing group. Okay, we have NO2. NO2, it has a positive charge on nitrogen and negative charge on an oxygen. Nitrogen is capable of making double bond with the ring, and if that one happen on the ortho positions and the pair position, we will have a positive charge. So what does it mean? It means when the electrophile is reaching the ring through the ortho or pair position, it will find carbon atoms that they are already depleted from technically electron density. So there is not much, electron density left there to share with the electrophile. And remember, the electrophile has a positive charge. So the ortho or pair position or pair carbon atoms are not the best to attack them because there is no electron density left on them. And the only one that is left untouched is the meta position. Meta position is here, either one, we did not have any positive charge on it, so that one left untouched. So I'm going to say electrophile will prefer the meta position. And so the addition, it will happen through the meta position, not the para or the ortho position. And so if you add the electrophile through the ortho position, you will have a positive charge on a carbon where nitro group already attached there. Okay. That's going to exaggerate the positive charge. So the positive charge is going to be extreme and it will go really, really high. What does it mean? Activation energy, it will go up, so the reaction will be slower. Okay. Reaction will be slower because we are exaggerating the positive charge. And now when it comes to the pair position, we get the positive charge here, but the positive charge, it can technically do resonance, and we can share that lone pair, that double bond with carbon. And if that one happen, we get the double bond here. Now again, we have a positive charge sitting on a carbon where we have electron withdrawing group there. And again, electron withdrawing group is pulling electron density to itself. So it's pulling electron density up. And we have positive charge there. And there is a group there that is trying to pull more electron density. That's going to exaggerate the positive charge on the ring, and it will make the intermediate unstable. And because it's unstable, again, the activation energy is going to go up. Now, how about the meta position? The meta position, and as you see, and it doesn't matter whether we are attacking the right or left meta position, that the positive charge is not going to show up on this carbon. It doesn't matter how many resonance structure you draw, the positive charge is not going to be there. And because it's not close to the nitro group, so I'm going to say we are not exaggerating the positive charge, or yes, you can say the nitro group still is pulling electron density because it still is far from the positive charge. I'm going to say the exaggeration here is not that extreme. And so the electrophile will see more electron density on the meta position rather than ortho or para position, and the attack, it will happen there. So in that case, we will get this. Mainly, we will get para. Sorry, nitro. No, my bad. we will get a meta product. So new NO2, it will show up here. This one is going to be around 93% of the product, plus something around 7%, either ortho plus para position. So ortho plus para position, something around 7%, while the meta position, meta is something around 93%. Okay, I'm going to replace the nitro group, which is a strong electron withdrawing group, by a weak one, like halide. Halide, they have higher electron density than other elements. So they will apply, pulling effect through induction. Okay. Now, halide have lone pairs, and because they have lone pairs, they can share it with the ring. And if that happens, we can have negative charges on ortho position or a para position. Okay, but not the meta. Okay, ortho or para position. When the electrophile is reaching the ring, it will find more electron density inside the ortho or the para position. Okay, so the addition is going to happen on ortho or a para position. Okay, and that's the reason we say halide, even they are electron withdrawing group, but because of the lone pair, and they can share lone pair with the ring, and they will technically create new resonance structure that they have negative charges on the ortho and para positions. And that means they will favor addition of the electrophile to the para or ortho position. So in this case, I'm going to say if we run the reaction, we will get this product. So one product is to get ortho product, say NO2, and the next one, it will be this one. Nitro, it will be in a para position. So this one, it will be ortho. This one, it will be para. Can I get a meta product? Yes, we will get meta product also, but that's, I think it's going to be maybe around 1 or 2%. And so the product is going to be either ortho or it's going to be actually both of them, ortho and para. Okay, ortho and para. Meta, we will get something really, really small amount from it, and it can be around 1 or 2%. Okay, let's talk about the transition state of addition of NO2, okay, NO2 to a ring with halide group. If the addition happened through the ortho position, and we will have a positive charge on a carbon that it has the halide, and a chloride, it can share lone pair with that carbon, and it will get the double bond. Now it will form a double bond with carbon. Now carbon is saturated and has no positive charge. The positive charge is on chloride. So carbon now super happy. That means the activation energy here goes down because the chloride managed to share a lone pair with carbon. And if the addition happened through the para position, positive charge, it will be there. But we can share that double bond with carbon that it has a positive charge. And if that happened, now we have a positive charge on a carbon that attached to the halide. Again, we can make a double bond. So chloride, it can share lone pair with that carbon. And if that one happened, we will get a double bond and between carbon and halide. And now, as like we said before, activation energy is going to go down and the reaction will be faster. How about the meta addition? If we attack through the meta position, the positive charge will not show up on this carbon, okay, regardless of how many resonance structure you draw, and you cannot bring the positive charge on that carbon. And because it doesn't show up there, halide cannot help carbon to stabilize the positive charge. And because that cannot happen, activation energy will go up and reaction will be slower. So addition through the meta position is not favored. Okay, this one is not favored, and this is the reason that I say we get really low product from the meta. So favored one, it will be nitro on the ortho or nitro on the para position, plus maybe 1 to 2% from meta position. Okay. And this is going to be the end of this lecture, and thank you very much.